All right, we're going to continue with section 10.2, last part. Today, we're going to take a look at the line integral of vector field. Okay, well, a vector field is like a force field. So I'm going to draw a vector field here. Let's say that we have actually, let's just do the curve C here first, right? Let's say that we have a space curve C. The C. Okay, we have a vector field. Vector field. Imagine that a particle moving along the curve C. The vector field pushes the particle to move in the direction of the tangent vector. To make life easier, we use the unit tangent vector instead. For a very small subarc, we can see what is going on here. Sample. We have forced, the vector field is the forced here. And what do we do here? We are moving a particle, so force dot distance. That is what we have here, but then we know force dot distance is the work. Distance here is just the unit tangent vector, so Ti. And ds. Okay. Where Ti is the unit tangent vector. This is the subarc, right? Subarc. ds is very small subarc here. You see that the vector field is gonna be, this is the vector field here. It will push the particle, of course, in the direction of the unit tangent. what is the integral, right? Sum them up along the curve C. F dot D. D is the T ds. Okay. Yeah. It is exactly the line integral of vector field. Parameterize this thing. You know, if you want to parameterize, you got to parameterize the curve C, right? You can only parameterize the curve C here. Okay. So a curve C here would be from, you know, A to B. We don't know. But I'm gonna keep it as the curve C just to make it look nice. Because the notation look pretty nice. F is gonna be a x, y, z, right? If you parameterize the curve C, then this is gonna be a f of or t. Yeah, that is how you parameterize x, y, z. Right? The unit tangent vector is the tangent vector, so that is the r prime t over the magnitude of r prime t. Right? It is the unit tangent vector, and then the ds here. You have to figure the ds. Well, last time we did the ds. Ds is the root of dx over dt square plus dy over dt square. So it's the x prime square plus y prime square plus z prime square dt. Okay. All right. What is this one? Square root of x prime square plus y prime square plus z prime square. This is the same as the magnitude of the tangent vector. You know, you can replace the C here by from A to B if you want to, right? Yeah, if you want to, you can just write A to B because it is exactly A to B. R prime T over the magnitude of R prime T. And then this is exactly the magnitude of R prime T dt. Okay. So what we have here is the integral A to B f of t multiply to R prime T dt. A nicer notation is the line integral of f dot this whole thing here dr. Oh yeah, A to B. Oh, how the heck did I write A to C? Now, sometimes it is false, sometimes it's vector is the same thing too. X squared minus xy in moving a particle along the curve C parameterized by cosine t okay, it is the curve C here. So it is just 1 to 1. The orientation or the direction of the curve C goes against the vector field. So we expect the work done to be negative or positive. We're going to fill this out later. Integral along the curve C f dot dr. Okay. Well, we got to parameterize this thing here. And then remember, when you parameterize, you can only parameterize the curve C. Luckily, we already did. Look at this thing here. It's already here. So it's going to be a f of RT. T go from 0 to pi of 2, right? I'm just going to write this here for the sake of the formula. But then in the next example, I'm not going to write this out, because you guys can do the substitution right away. F or T, just be careful with the substitution here. Look at the vector field F right here. It's x squared. It's the first component, and then minus xy. So x is cosine t, so it's going to be a cosine t squared and then minus cosine t sine t. Okay, dot r prime t. This is r t here. The r prime is gonna be negative sine t, cosine t negative sine t cosine square t and minus sine t cosine square t. Oh, how nice. dt. I'm gonna move out the -2 outside, and you can just keep -2. Doesn't matter. If 2 sine t cosine square t dt, and then next just a substitution. Use up. The derivative of cosine is the negative side, so that's going to take care of the negative right here. And then u 3/3, so that's going to be 2 cosine 3t/3 0 have 2. Okay, oh, what do we have here? Answer is supposed to be negative. I guess it goes again, but then you see 2/3 cosine pi/2 to the power 3 minus cosine 0 to the power 3. Okay. 2/3. This is the cosine pi/2 is 0 minus 1. So the answer here is negative 2/3. As you can see, yeah, it does explain when you sketch out the vector field and the curve C. Well, the orientation of the curve C goes against the vector field. Therefore, the work done is negative. Okay, you come up. Find the work done by the vector field. Equal. X squared plus y squared. Three xy in moving a particle from in the direction of a line segment from 0, 0, 2, and 1. The reason why I give you guys the vector field only have 2 components is because it's easier to sketch out the curve C. So you can get an idea of what is going on. Okay, you can think about this one, and I'm gonna use the GeoGebra to sketch out the vector field from 0, 0 to 1, 1. Okay, what do we see here? Okay, so here the parameterize is pretty simple. Most of you already know the formula, hopefully. If not, I'm just gonna rewrite out a few times, and then you'll be able to remember that formula. Well, this is just a line segment here, so actually I'm gonna write it right here. X equal to well, x naught plus t x1 minus x naught, y is equal to y naught plus t y1 minus y naught. And if you do the substitution, you see this is t, right? So from here, you get the odd t. T. Yeah. Okay. And then make sure that you know that when you do this kind of parameterization, right, t is always between 0 and 1, which makes life very simple. 0 to 1. Okay, f, I'm gonna do a substitution here. Look at this f, x squared plus y squared times 3xy. So that is, would be x squared plus y squared, and then the other one is going to be a 3xy 3xy. Okay, dr is all prime t, so all prime t is derivative of this is 1 dt. We have a 2t squared plus 3t squared dt, so that is going to be a 0 to 1 5t squared dt, so this will be a 5 over 3 . Using the vector field or the force field, F equal to yz xy xz along the path or t square t to the fourth for 0 less than equal t less than equal 1. Okay, so here come the vector field. Difficult to see. I'm just gonna have to bold it so that you see. Okay. If you work it out, the answer is the 131 over 140. Nice note to close up, what exactly are we doing here.